the new material, how is your calculus, and how are you doing at new problems as well as algebra. So one of the reasons I like the third problem is it's a good way to test and see where your algebra skills are at. One of the most common mistakes people make is not calculus mistakes, but actually algebra mistakes in doing the calculus. And so if you had trouble with the last problem, this is probably a good indication that we should chat either one-on-one or with the TAs, Math Science Resource Center people, about your algebra. Quick announcement, if you have paperwork or forms or things that I'm supposed to have, you need to get them to me sooner rather than later. You don't want to get into the habit of doing things at the last minute. You don't want to get in the habit of handing in homeworks late and asking for extensions. I told the previous class the story of the Williams student who lost a job with one line. And so one of my colleagues had set up an interview for one of her students in New York City. The firm responds and says, I will see you at 8:30 a.m. at the following place. The Williams student responds, oh, I'm not a morning person. Let's meet in the afternoon. One would think that this would be obvious not to do this, but based on what happened, I am now warning all of my students not to do this. I thought it was acceptable to tell the company, I'm coming down from Williams. If we could make the meeting in the afternoon, that would be better for me, but if not, I will be there at 8:30. I've been told by my contacts in industry, you don't even say that. It's, thank you very much, I will see you at 8:30. I want you to get into the habit of doing things right, doing things on time, so that years from now, I don't tell stories about things that you did. If you want to know stories of things that I did that were stupid, I'm happy to tell them, but not while the camera is rolling. Okay, so what we're going to do today is we're going to talk about what is the correct definition of the derivative in several variables. And we're going to use our knowledge of one variable calculus, not surprisingly, as a motivation. But to give you a sense of what things can be like, is I want you to consider the following example. Let's let f of xy be the function xy to the 1/3. And let's note that f takes two inputs and gives you one output. And I'm going to define a function g from R to R2 by g of x is x comma x. So g takes one input and returns two outputs. Notice that f wants two inputs. So it makes sense to talk about f composed with g. So we'll define this new function h to be f composed with g by h of x is f composed with g of x. So that's f of g of x. That's f of xx, or x to the 2/3. OK. So h is some function from R to R. We haven't really talked about what it means for a function of two components to be differentiable. But if you look at the function g of x is x comma x, both x and x are nice functions. The derivative of x is 1. This function g should be differentiable. Let's look at the function f. So let's say I want to calculate the derivative of f with respect to x at the point 0, 0. Well, by definition, it's the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. So it's the limit as h goes to 0 of, sorry, these need to have two components. Minus f of 0, 0 of h. That's the definition of the derivative of f with respect to x. So we have, this is the limit as h goes to 0 of f of h0 minus f of 0, 0 over h. OK, well, we can just substitute in. F of h0 is just going to be h times 0 to the 1/3 minus 0 times 0 to the 1/3 over h. What does the numerator equal? I think I heard it from over here. What does the numerator equal? 0. The numerator is always 0. So I have the limit of 0 over h, so I just get 0. So we're in a situation where df dx exists, df dy exists. This function g is nice and differentiable. Well, let's look at this function h. H prime of x is d by dx of h of x. This is d by dx of the function x to the 2/3. What's the derivative of x to the 2/3? Yes, as that person has realized, the derivative is x to the minus 1/3, and it is not differentiable. Let me see if I can console them. It's okay, we'll find differentiable functions later. All right. Not my kid, fortunately. Okay, so it is horrible. It is absolutely, there's nothing we can do about it. This poor, poor function is not differentiable at the origin. It just blows up. But if you look over here, everything is so nice. G is differentiable, and the partial derivatives exist. It's coming down a little bit. Okay. So unfortunately, nice plus nice is not always nice. The question of what does it mean for a function to be differentiable in several variables is more subtle. In one variable, it's kind of easy. You know, there's only one way to approach a point, and so if df dx exists, well, that's the derivative. In several variables, I have to be able to approach in many different ways. And so here, what's going on is everything is fine if we approach along the coordinate axes. But if we approach along the 45-degree line, things blow up. And so having the existence of the partial derivatives is not enough to imply that the function is differentiable. So we need a notion of differentiability in several variables. And so the goal is to get to that notion. And so to get there, I want to take the notion you have of the derivative in one variable and recast it in a way that will generalize much better. So let's do a quick review of tangent lines. So if I take some function, here's the point x0, this is the point x0, f of x0, and the slope is f prime of x0. We can write down the tangent line. So the tangent line is y minus y0 is m x minus x0. Or y minus f of x0 is f prime of x0 x minus x0. Or y is f of x0 plus f prime of x0 x minus x0. And the way you should view this is where you started. This is your instantaneous speed. This is how much time has elapsed. So if you travel at a constant speed for this amount of time, this is how much you've changed. And so what we want to do is we want to quantify how close is the tangent line to the original function. And the idea is that as long as x is close to x0, this should be a pretty good approximation. So I claim f of x is f of x0 plus f prime of x0 x minus x0 plus a small error. And I want to figure out exactly how small is that error. So let's look and see what's going on. So if we look at f of x minus f of x0, I want to figure out how large can that error be. So one of my favorite theorems in Calc 1 is the mean value theorem. It's amazing how useful the mean value theorem is. You're not supposed to have seen Taylor series, but we will see Taylor series later in the semester. One of the key tools in studying Taylor series, as well as studying the proof of the fundamental theorem of calculus, is to use the mean value theorem. It allows us to quantify errors. So the mean value theorem tells us that f of x minus f of x0 divided by x minus x0 is f prime of c for some c between x0 and x. The way you should view this is your average speed in the interval. This is your instantaneous speed at some time. And what the mean value theorem is saying is that if your function is nice, at some point in time, you must be traveling at your average speed. Imagine your average speed is 50. So average speed equals 50. If at every moment in time you're traveling at less than 50, then your average could never be 50. Conversely, if every moment in time you're traveling faster than 50, your average could never be 50. It would have to be higher. So at some moment, you must be traveling at the average speed. So this is a very useful result. And we can actually rewrite this as f of x minus f of x naught is f prime of c times x minus x naught. Or equivalently, f of x is f of x naught plus f prime of c x minus x naught. All right, well, if you look at this, this looks very similar to the tangent line. What's the only difference between this and the tangent line? I'm sorry? In what sense? The tangent line doesn't have any error. The tangent line is an exact.
The slope for f of c.
Okay. So we have f prime of c versus f prime of x naught. That's the only difference. This is the actual value of f of x. This is the approximation. So we want to see how good is our approximation to the actual value. And so the error in the tangent line approximation is f of x minus y is f prime of x naught minus f prime of c times x minus x naught. Okay. Any thoughts on what we could use to try to estimate the difference between f prime of x naught and f prime of c? I want to get a sense of how big is that difference. What could I use? Hint, it's on the board. What could we use to try to estimate this difference? Mean value theorem, right? I love the mean value theorem, right? Why would I use it just once and stop, right? We have how many minutes to fill up today? We've got lots of time, right? If you look at the mean value theorem, we used it to estimate how far f of x and f of x naught were. Well, let's apply the mean value theorem again. But now what function do we apply it to? Apply mean value theorem to what function? Instead of applying it to f, we should apply it to so looking at this, what function should we apply the mean value theorem to? Yes? F prime, right? And now the mean value theorem says f prime of x naught minus f prime of c over x naught minus c should be f double prime of some point d with d between x naught and c. And so this gives us that f of x minus y is f double prime of d x minus x naught x naught minus c. So if I take absolute values, the error in my tangent line approximation is f double prime of d times x minus x naught squared as x naught minus c is less than equal to x naught minus x. So here's x naught, here's x, here's c, here's d. So this distance here clearly can't be more than the whole distance x naught to x. So what this tells us is the difference in the tangent line is like the second derivative at a point times the difference squared. So if x minus x naught was 1 over 100, this would be like 1 over 10,000. So not only is it a good approximation, It's a damn good approximation. The error is going to be essentially the square of how far you've moved. We can rewrite this. Rewrite the definition of the derivative. So consider the limit as x goes to x naught of f of x minus f of x naught minus f prime of x naught, x minus x naught, divided by x minus x naught. So what I'm doing is I'm taking the function, I'm subtracting off where I am, I'm then subtracting off my instantaneous speed times how much time has elapsed, and I'm dividing by how much time has elapsed. According to what we've just done over here, if my function is nice, if it has two derivatives, this quantity is going to go to 0. Because the numerator is going to look like some constant times x minus x naught squared. The denominator looks like an x minus x naught. This is going to get very small. Let's imagine we're in a situation where this limit equals 0. I'm going to show you that this limit being 0 is the same as my function being differentiable at x naught. Well, when you look at it, we have the first piece and we have the second piece. The x minus x naughts cancel, and we have an f prime of x naught. Does f prime of x naught depend on x? As I vary x, does f prime of x naught change? No. It's always fixed. I can take the second part out of the limit, and I get the limit as x goes to x naught, f of x minus f of x naught over x minus x naught minus f prime of x naught equals 0. Because again, the x minus x naughts cancel, the f prime of x naught has no x dependence. All right, well, this is the same as f prime of x naught is the limit as x goes to x naught, f of x minus f of x naught over x minus x naught, which you might feel more comfortable writing the limit as h goes to 0, f of x naught plus h minus f of x naught over h. That's our old definition of the derivative. So saying this equals 0 is the same as saying my function f is differentiable at x naught with derivative f prime of x naught. Now, when you defined things in Calc 1, they did not define the derivative this way. If they did, I apologize. Okay? But this is a much better way of defining the derivative when you want to do things in several variables. Because we have to now consider all these different ways of reaching a point. We have to consider all the different Kamm-Kahler paths. These two definitions are equivalent. And this suggests what the correct definition is for the derivative. So I'm going to erase the announcements. If you haven't picked up your exams, please do so after class. I've put in the new homework problems that are due on Monday. There will be no Sable lunch. I am recovering. If you want to risk it, I will be in my office from 2 to 5 today. If you want to just phone in with a question, that might be safer. I'm not sure how infectious I am. Okay. So definition of the derivative. We want the limit as x goes to some point a of here's where I want to be, f of x. I subtract where I start, f of a. And now I do df dx1 at the point a times x1 minus a1 minus dot 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 minus df dxn at the point a xn minus an. And then I divide by x minus a. And I want this to be 0. So this is the definition of the derivative. Or this is what it means for f to be differentiable. there's a small mistake in what I wrote. I did something illegal. So I want you to be able to look at equations and see when they're right and when they're wrong. I've done something here you can't do. I blame the drugs. Many of them. I'm not sure which. What have I done that's illegal? I mean, it looks fine to me. It actually looks blue. But what have I done that's wrong? What kind of quantity is the numerator? Numerator just a number. F of x, that's the value of where I am at x, minus f of a. Yeah, numerator is just a number. What about the denominator? It's a vector. What does it mean to divide by the vector 1, 5, 8? I don't know what it means to divide by a vector. I can't do that. So we have to go back to what was going on in one variable. But you know what? If I put in absolute values, does that really change anything in one dimension? No. I mean, if the whole thing is supposed to tend to 0, the absolute value will tend to 0. And now I can put an absolute value in the numerator, and I'll take the length of the vector in the denominator. That's the correct definition of the derivative. We're not going to do too much with this, but in my book, there would be something wrong about teaching you multivariable calculus and not actually giving you the definition of the derivative in several variables. This is the definition. We now have the notational mess of the derivatives. So notation. F sub x means d by dx of f, or big D sub x of f. This is the derivative of f with respect to x. This is actually good notation. In one variable calculus, how would you talk about the derivative of the function f of x? What would you often say? You have the function f of x, its derivative is f prime of x. That's bad notation in several variables. I have several different variables to take the derivative with respect to. If I say f prime, well, take the derivative with respect to what? That's why we put the subscript x down here to tell us take the derivative with respect to x. Then we have the full derivative. Big D of f is upside down triangle of f. It's called the gradient of f, and we write grad f for the word gradient. And this is the vector df dx1, df dx2, dot, 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 df dxn. And so that's going to be the full derivative. So note that if f has n inputs and 1 output, then the derivative of f has n components. Well, that's reasonable. My function has n different inputs, and I want to know how is it changing with respect to all those different components. How many of you have taken a physics class? Okay, so you've got your position. The derivative of position is speed. Derivative of speed is acceleration. And fortunately, in physics, we usually don't have to go beyond acceleration. We typically don't have to go beyond 2 derivatives. Well, it seems reasonable we're going to want to take derivatives of derivatives here. So the question is, what does fxy mean? Is it d by dy, d by dx of f, or d by dx, d by dy of f? Both are reasonable. Do I read from the outside in, from the inside out? This is notation, right? The notation we like to use is we like to start on the outside and move in. It is d by dy of f of x, which is then d by dy, d by dx of f. Okay. Sadly, the universe did not listen to you when you requested the product rule. If you could request a theorem about the second derivative, what would you request? What thing would you love to be true about fxy? Yes.
You say you'd want it to be fyx.
Yes. Right? Then you don't have to worry about remembering which way you're supposed to take the derivatives. If you could choose your theorem, this would be a theorem you would love to have. It basically says the order in which you differentiate doesn't matter. Who thinks this theorem is correct? Sadly, the theorem is not true, but it's almost true. False, but not by much. Is true if f is twice continuously differentiable. So it would take us a little bit far afield to give the proof of this. I've included a proof of this in my lecture notes online. If anybody wants to, I'm happy to meet with you and go over a proof of this. If you're considering a math major, you do want to see proofs of results like this. Most of you are not there, so I would rather spend the time doing more examples and covering things like that. But it's nice to know that these things can be proved. So this means we need f, fx, fy, fxx, fxy, fyx, fyy to be continuous. So if all of those are continuous, then we do have the equality of second derivatives. F of xy is f of yx. And then you don't have to worry about which way is which. Okay. So from the definition of the derivative, we actually get the tangent plane approximation. So tangent plane. Let's let z equal f of xy and z naught equal f of x naught y naught. So tangent plane at x naught y naught is the following. Z is z naught plus df dx at the point x naught y naught x minus x naught plus df dy at the point x naught y naught y minus y naught. This is a really good approximation to our function. If you think about what's going on, if you come back over here, this is the definition of the derivative. This is exactly what we have in the numerator for a function of two variables. And the whole idea is in one variable, the tangent line was supposed to do a really good job approximating the function. The tangent plane is supposed to do a really good job in two variables or higher variables. If you think about it, and I can replace the point z naught with f of x naught y naught. If y is fixed, then we would have z is f of x naught y naught plus df dx x naught y naught x minus x naught. This is the tangent line in one variable. So if I fix y, I have a function of just one variable. This is the tangent line approximation. This is where I start. This is how much I move. If x is fixed, what do we have? We have z is f of x naught y naught plus df dy x naught y naught y minus y naught. So this is my tangent line approximation if x is fixed and y changes. It almost looks like I'm just adding the two. The only reason I'm not just adding the two is I don't get this twice. So why should I not be getting this twice when I combine? So if you think about what the tangent line is saying, this is where you start, and this is how much you move. This is where you start, this is how much I move. If I want to combine them, I'm not going to add my starting point to my starting point. This is where I start, this is how much change I have from the x, and this is how much change I have from the y. And so this is the tangent plane formula. And so if I give you a function of two variables now and I give you the initial point, you can now calculate everything and you can find the tangent plane. And just like the tangent line does a great job approximating a function, the tangent plane will do a great job approximating a function of several variables. And you can look at this as basically building on the tangent line. And we're basically just doing it in each direction, saying, I start here, first I do my x motion, see how much I change, then I do my y motion and see how much I change. And I basically just add those two to each other. And as long as you're very close to the point x naught, y naught, this is going to be a really good approximation. Okay, but the key from all of this stuff is we took our notion of derivative in one variable, we generalized it to the notion of the derivative in several variables, and really what we're doing is where we are is where we were plus a small change, and that small change is coming from the different partial derivatives. The main theorem in the subject, which I'm not going to prove in class, but I have included a proof in the notes, is basically what information tells you what. So this is the main theorem. So partial derivatives exist and are continuous implies the function f is differentiable, implies the partial derivatives exist. So these are the main implications in the subject. And it turns out going backwards, you can always find a counterexample. I can find a function where the partial derivatives exist, but the function is not differentiable. I can find an example where the function is differentiable, but the partial derivatives are not continuous. From the beginning of class, we looked at the function f of xy as xy to the 1/3. I strongly urge you tonight to go home and see, is that function differentiable? Are the partial derivatives, do they exist and are continuous? So I'm not going to prove this thing, but I want to talk a little bit about why it's reasonable. Well, think about what it means for function f to be differentiable. Notice that we have in the definition of differentiability the partial derivatives, right? So if my function is differentiable, clearly the partial derivatives exist. I wouldn't even be able to write this down. All right, so if the partial derivatives exist and are continuous, the fact that the function is differentiable, that's a big theorem. It's not at all clear that just because these partial derivatives exist and are continuous, that this limit is going to be 0. This is a bit technical. If you want to see the details, it's in the notes online. Going from here to here, that's the main meat of the theorem. Going from here to here is trivial, right? If the partial derivatives exist and are continuous, can you show the partial derivatives exist? Right? That's not that bad, right? That's essentially by definition. Okay? So the difficulty, the real meat, is going from here to here. And all the reverse arrows can fail. Okay, so that is the big theorem of the subject. I am erasing the definition. We will try never to use that definition again. But, this is a math class. And you should see, the statement, done at least once correctly as to what does it mean for a function to be differentiable. Whenever you take a class, you do want to understand what are the key ideas to get out of it. Sometimes it's I want you to get techniques and methods, but there are also results. So one of the exam questions was on the fundamental theorem of calculus. If you've taken a Calc 1, Calc 2 class and can't state the fundamental theorem of calculus, there is blame to be assigned either to you, to your teachers, mixture, the community, whatever. But you should know the key result in a class. In all the classes you're taking right now, it shows you what is the point? Why am I taking this class? Hopefully there will be a good answer. Okay. So what I want to do now is talk a little bit about properties of the derivative and then end with some examples. So properties of the derivative. And so we're going to have f from Rn to R. We'll have g from Rn to R. And the first is the constant rule. If a of x is c f of x, then the derivative of a at x naught is c times the derivative of f at x naught. So basically what this is saying is if I rescale my function by a factor of 5, I change all the partial derivatives by a factor of 5. So unwinding it, it's dA dx1 is just c df dx1, dA dx2 is c df dx2, and so on. Bless you. Bless you. Okay, so hopefully the constant rule is reasonable and clear. I will see if we have a screaming baby again in a moment. I'm not sure what they're moving on to. So next is the sum and the difference rule. So let's let a of x be f of x plus g of x. Then the derivative of a at x is the derivative of f at x, well, I guess we're doing it x naught, plus the derivative of g at x naught. So again, the derivative of a sum is the sum of the derivatives. And unwinding it, dA dx1 is df dx1 plus df dx2, dA, I'm sorry, dg, sorry, dg dx1. dA dx2 is df dx2 plus dg dx2. So the derivative of the sum is the sum of the derivatives. And again, you would just get this by looking at things component-wise. All right, things will get a little bit more interesting now. So I'm not quite sure if the labeling is correct or not, but product rule. So a of x is f of x divided by g of x. Oh, I'm sorry, f of x times g of x. Then dA at x naught is df at x naught times g of x naught plus f of x naught times dg of x naught. All right. Formally, this looks very similar to what we've done before. If I unwind it, dA dx1 is df dx1 g of x naught plus f of x naught dg dx1, and so on and so on and so on. So let's see why this is true. So I'm going to prove the product rule and not the sum constant, because the proof here is a little bit more involved, and we'll show you a little bit of what's going on with vectors. And then we'll do an example and see whether or not this rule is worth knowing. So let's calculate dA dx1. This is d by dx1 of f of x g of x. All right? How do I take the derivative of f times g with respect to x1? What rule do I use? So what rule do I use to take the derivative of this product? the product rule, right? Sometimes the hardest questions are the ones that almost sound like by definition, isn't it the product rule since it's the derivative of a product? Yes. We have lots of other variables, but whenever I say d by dx1, that means the other variables are fixed. So I only have something as a function of one variable. All right? Well, by the product rule, this is df dx1 times g of x plus f of x times dg dx1. Similarly, dA dx2 would be df dx2 times g of x plus g of x, plus f of x times dg dx2. And I can just keep going and going and going. And so if I put all the pieces together, dA at the point x naught would be, okay, first component is df dx1 g of x naught plus f of x naught dg dx1. Next component, df dx2 g of x naught plus f of x naught dg dx2 dot dot dot. And when you look at this, all the components have two pieces. The first piece is always multiplied by a g of x naught. The second piece is always multiplied by an f of x naught. So I can write this as some crap times g of x naught plus f of x naught times something else. Right? Because all these pieces have a g of x naught. Just pull it out. And the sum of two vectors, well, I can just write it as one vector plus another vector. Well, what is this crap over here? It's df dx1, df dx2, df dx3. Oh, that's just the derivative of f at the point x naught. And over here, it's f of x naught times the derivative of g at the point x naught. And so this is just the product rule. So, again, what's nice is all of these rules for several variables, they follow immediately by looking at things in one variable. So let's go back to one variable calculus, go back to the product rule, go back to the sum rule, go back to the constant rule. And now just remember that you have components, or you have more than one way to take derivatives. So the first component is coming from the derivative with respect to x1, the derivative with respect to x2, and now we can just group things together. All right, so let's end with an example. I'll leave this up here. So let's take example. Let's let f of xy be x squared plus y cubed. G of xy is x times y. All right. The derivative of f at xy is going to be df dx, df dy. What's the derivative with respect to x? So derivative of f with respect to x. (2x), good. And with respect to y, 3y squared. All right. dg xy is dg dx, dg dy. All right, so the derivative of g with respect to x is just going to be y, and then the derivative with respect to y is just x. So dA at the point xy is supposed to be df at the point xy times g of xy plus f of xy times the derivative of g at xy. All right, so what's the derivative of f at xy? That's going to be 2x 3y squared and g of xy is just xy, plus f of xy is x squared plus y cubed. Now derivative of g at xy is just yx. All right, so we need a little bit more space. So we have two vectors. Each vector is being multiplied by a function, so let's just simplify a little bit. So dA at xy, the first piece is going to become, I think, 2x squared y. And the second piece is going to be 3xy cubed. And the next one is going to be x squared plus y squared. I'm sorry, x squared plus y cubed times y. Well, we need even more space, great. And then x squared plus y cubed times x. So collecting, we get 2x squared y plus x squared y plus y to the fourth, just multiplying this out, 3xy cubed plus x cubed plus xy cubed. And so just collecting and simplifying, we get, I think, 3x squared y plus y to the fourth, 3xy cubed plus x cubed. Oh, but we have the xy cubed, so this becomes a 4. All right. There's the answer. This is obviously one of the most important functions in all of mathematics. This function occurs throughout all of mathematical physics, right? This is a make-work example. How can you tell if we calculated correctly? So again, you want to try to find alternative ways to do a calculation. Is there any other way we could have taken the derivative of the function a? What's the function a? So for this problem, what's the function a? F of xy times g of xy. Okay, so a of xy is f of xy, g of xy. Well, f of xy is x squared plus y cubed. What's g of xy? Xy. So it's the function x cubed y plus xy to the fourth. How would you rather take the derivative of this function? I would never use the product rule here. I would just multiply f and g and take the derivative, right? I deliberately wanted to do an example this way because we had 6 minutes to fill, and so I needed to I wanted to just show you how you would use the product rule. There will be times when you will not want to multiply things out together like this. But this is a great way to check. So dA xy is dA dx, dA dy. So when I take the derivative with respect to x, I get x cubed plus 4. Hopefully, this is not looking, oh, I'm sorry. When I take the derivative with respect to x, I get 3x squared y plus y to the fourth. Now when I take the derivative with respect to y, I get x cubed plus 4xy cubed. And that does match, I think. I have these in a different order, but that doesn't matter. Okay. And so this is a good way to check and see that everything is fine and consistent. So again, always try to find another way to calculate an answer. Is there another path? On one of the exam questions, you're looking at cos squared minus sinh squared. There were two different ways of doing this. A lot of people, the way I thought to do it is just roll up your sleeves and do the algebra. Other people thought of factoring. And if you can find multiple ways of doing a problem, you have a much better chance of catching your error. Sometimes the different approaches also give you a better perspective or a different perspective that's more valuable for one thing rather than another. All right, so we will continue. We've basically finished section 12.4. We will do some fun applications of these multivariable results later. We'll do a good chunk of mathematical statistics. We'll do Newton's method, and then we will continue on Monday.